Curve fitting is a really important technique to understand when you have a series of data points and you want to understand the trend that that data has. Well, in this video, we're going to show you a hands-on workshop where I demonstrated 5 different types of curve fitting at a curve fitting workshop. And the types that we did were linear least squares, a weighted least squares, a nonlinear curve fit, data smoothing using LOESS, as well as multivariable curve fitting. If you've never tried these before, then you can go ahead and do that now. You need DataGraph for Mac OS to do this. Follow along with us. The links to the data sets are in the description of this video, and the data that we used a couple of different data sets from the National Institute of Standards and Technology. And the first one that we're going to do is the linear least squares. However, the video is divided into chapters, so if you want to skip to a particular type, then go ahead and do that. You don't have to watch it from beginning to end. But the video starts with grabbing some data from the NIST website and showing you a little bit about the example that we use for the linear least squares. Here it goes. You have a link to this handbook, and you can see over on the left-hand side, there is a number of different chapters. The information that I'm using is mostly from the modeling chapter. And there's also a page that just has a lot of different data sets. And so that this is a link to the main chapter. I'm going to send you a link to this specific page. And this is the first example that we're going to do with linear regression. This is a worked example. And that's why I thought this would be nice, because even if I don't describe all of the background on this, you can go to these web pages and get more information again on the methods and curve fitting and compare what you're doing in DataGraph to what's here. But this is a set of data, Alaska pipeline example, where they were doing a calibration of some data. And if you go to that last link that I sent you, and then go to this section, background and data. Give you a moment to get there. And you'll see a set of data. You can also click, there's a link here to a text file that if you click that will bring up a file that looks like this. This is, they use a similar format for a lot of the data that they have on this website. And so what I want you to do to start off is just to select this. So I just selected, notice where I'm selecting this. I'm not going to take all of this right now. I'm just taking the X and Y headers, the name batch, and I'm just copying this. So this is not a huge data set. You can say edit copy, and then go to, oops. Let's see, here we go. Go to DataGraph. Oh, I had DataGraph on my other screen. Sorry about that. So here I am in DataGraph. I actually want to put this on a new desktop. There we go. Okay, so I'm in a brand new DataGraph file. I copied the data from this website. Once I'm in DataGraph, I don't even have to click anywhere. I can just say edit, paste. And now I should have these columns of data. Okay, I'm trying to pause a little to make sure that everyone can sort of keep up with what I'm doing. Now, one thing that DataGraph does whenever you paste data in or import data is it's checking to see what the data type is. And what you'll notice by looking at the icon here and also the little symbol here for this column, it has a little AB there. That indicates that it thought that first column was text. And this, perhaps in the next version of DataGraph, we should be a little more discriminating. There's really just this one row of text here, and it's assigning this whole column to text. But we can easily deal with this because this should be a number column. If we're going to do curve fitting and plotting, we need this to be a number. So you can just go to the gear menu on this object and say convert to number column. And now that row that has the text in it shows up as red because it's not a number, but that's fine. If you want to get rid of that row, you can just select it and then hit the delete key, and then that'll be gone. So I should end up with 107 rows of data within my data graph file. And the next thing that I'm going to do is, it's convenient when you're plotting to always have the X on the left and the Y on the right. So I'm going to drag my X column over to the side. And the commands that I'm going to use right now are these two right here, which are in the default toolbar, the points command and the fit command. Quickest way to add this to a graph and to do the linear fit is to select the two columns. So I can hold my shift key, select the header for X, header for Y, and now I'm going to click the, so I've just selected my data. That's all I've done so far. Now I'm going to click on the points command. Now I can see the data, and now I'm going to click the fit command. And even though I didn't have the data selected again prior to clicking the fit command, there's logic in here that says if you've just plotted this data, you're going to add a fit, you probably want to fit the same data. So that auto-populated all of my menus where I had to select my data. And okay, so that's it. I mean, here I've done my linear fit, but what I want to do now is I want to give you a little bit of a tour of some of the functionality that is in the fit command. So the first thing that I will do is I'm going to hide my side panel. I'll do Command D to do that. And now I want to shift my commands to the left-hand side and swap where the data is to give me a little more room to show you things. So for that, I'm going to do Shift Command D. And now my UI looks like this. The fit command itself has a bunch of different fitting functions in it. And these, I'm going to talk about LOESS fitting. We're going to do a nonlinear fit. And for this one, I'm also going to do a weighted fit. But first of all, some of the common things that, what do you want to do when you fit some data? Well, you want to know what the goodness of fit parameters are. So in data graph, there's a table within the command. So if I expand, open the command itself, you'll see here's my slope, here's my intercept, here's the standard error on these fit parameters, here's my R-square value, root mean square error, and my sample size. On the graph itself, if you want to see this information, then that's certainly a common thing that people want to do. So let me just show you, for example, one technique that I use all the time, which is to add a text command. Oh, actually, let me take that back. Before I do that, let me just add a legend and show you what happens when I do that. So I'm just going to click the legend command shortcut that's in the toolbar. And that actually will add the equation itself. I can click to drag this out. If I want to anchor this, I'm going to put this over in the upper left. I can put that here. This is something that's draggable. But say I also want to add, I show the R-square value, for example, or actually, let me do, I could do either of them, the root mean square error. So to do that, you'll notice that in every command, there is a legend name option. And this is what it is displaying. It's displaying the equation, the Y label are all being displayed here. So if I want to add an R square, for example, or the RMSE, the error for this, I can select, so what did I do? Let me do this slower, make sure you see this. Click this plus icon. When you do that, you get a menu of all the different things that you can display here. Oops, I clicked the wrong one, but I click that, and then I'm going to pick that I want this term, RMSE. And I can do this in other text boxes as well. I could put it in the title, but that is sort of convenient just when I do that a lot, where I just show, I add it to the display that's already there. So any questions on that? Or where's my tea? Here's my tea. I have multiple teacups. Okay, so the next thing that I wanted to show you was a little bit more on in terms of evaluating the goodness of fit. You have the R square, you have the RMSE. This is a pretty good fit of this data. It's R square is 0.89, but I can also view the residuals. And this is something that's built into the fit command. So if you go down to the bottom, there's a place where you can expand this, where you see this display of the residuals across the X range. And ideally, for the assumption for linear least squares regression is that you have a uniform set of residuals across a set of data. And the NIST handbook talks about this in detail. So I'm not going to go into it into a tremendous amount of detail, but what you see here is that you don't have that assumption in this underlying data, that in fact your amount of error spread is much higher for your X values than it is at your low X values. And as a result, your fit of this data towards the origin maybe isn't as good as you would like it to be. So if you use the loop tool, for example, and you zoom in on this, you can see where, well, you know, these points are influencing quite a bit where this line is going, more so than these points at the bottom. And if this should go through 0, for example, it's clearly the line is not doing that. And let's see, what else do I want to say about least squares? So, I mean, that's how you do a least squares regression. This is how you can view the results of it. And here's how you can you can look at the residuals. Oh, the other thing I wanted to show you was this functionality for outliers. So you want to make sure that the data set you're using, that it makes sense to do this, but you do have this checkbox here. So right here, there's a checkbox where you can remove and fit outliers, and that will look at the distance to the fit line, and it will remove outliers based on that. And you can change the amount of the standard error that's used as that reference point. Now here, I would not recommend really using that approach, although there's some outliers here. It's not like there's a clear benefit of that, but I'll do a really quick example just to illustrate this. So if you just want to, let's see, let me add a number column. I'm just going to do something really simple here where I do 1, 2, 3, 4, 5, 6. And I'm going to, I have a new graph. I'm going to do points and fit. This is a perfectly straight linear line. Therefore, my R square is 1. My error is really, really, really low. And yet, let's say I have, and if I look at the residuals, this is basically just all machine precision. These are tiny, tiny, tiny numbers. It's all 0. But if I take one of these points and I say, okay, it's 40. So now it's really far away from the rest of the data. This is an example of if I use this outlier approach and click that, you see now how this outlying point is no longer included in the regression. And you can visualize it right here because it shows you these green lines are showing you that points outside of that green line are not going to be included in the fit. So the fit command on its own, calculates these certain goodness of fit parameters. If there's things we're missing here that you'd like to see, I know we need to add just plain R instead of also in addition to R square. If there's anything else we should have that you think is missing, let us know. but I want to move on and I want to talk about how to do the weighted least squares fit. So if we go to the, let's see, go to the NIST website. Here it is. Come back here. They talk about this for this data set. So if I go to the Alaskan pipeline model, you can go to section 5 where it has weighting to improve the fit. And again, they go into a lot of detail here. I don't really have time to go through the derivation of the weighting parameter. They talk a lot about this, and that's what they're plotting here. If anyone's interested in that, let me know. And I've sort of worked through this. But basically, they recommend a weighting parameter, and they show what it is right here. So this graph is doing a weighted fit, and it's using 1 divided by whatever the value is for x to the power of 1.5. That's what that means. So to do this in data graph and to mimic the weighted fit that they have here within the NIST Handbook, what we need to do is we need to calculate or have the weights in a column, because basically, if you look within the fit command here, there is a menu option for weight. Currently, it's set to uniform, but you can use this to select a column of weights that's within your data table. So I'm going to actually take this graph and let's keep this one. So this is the linear graph. I'm going to make a clone of this rather than starting from scratch. To do that, if you've never done this before, there's these little buttons right here. That's a clone option, which will make an exact copy of the graph that you've already created. And now this one, so again, that was that button there that I typed. And this is going to be the weighted. And question, can we display these particular outliers in the plot? Oh, that's a really good question. I deleted that. Let me bring this back. It's easy to redo what I just did. So if you want to know which ones are the outliers, actually, this was something I wanted to show you. So thanks for asking this. In the gear menu, if you go to the fit command and click on that gear menu, there's a number of things that you can extract. And oh, maybe we haven't added this. Select outliers. So yeah, I thought we had added this, but I don't see it now. Residual fit, unless it's the, oh, okay. So here's how you can get what they are. That might have jumped a little bit, but let me, so if you go to the gear menu and you say extract column and you say fit, that's going to, or actually probably any of these, if I ask for the residuals, sort of annoying that it's popping that up nowhere, and I do want that closed. Will it show me all that? Yeah, okay. So basically what it's doing, let me delete some of these, we don't all these, is in this gear menu, when you extract a column, this is going to extract for you the values that are used in the fit. So you can see that this is the row that was selected as, that was identified as an outlier. It's not used in the fit. But it would be nice if it just had like a 0 and 1 indicator of when something was an outlier. I might be confusing that because I think we added that into the box command, but not into this yet. And I think that we should have that as well. So there is a way that you can identify when, you could, I won't go into it here. You could use a mask and do a little bit of footwork to specifically identify those rows. But I guess the easiest way just to see where those rows are is to go to this button here that says select outliers, and that will pop you to that row. So here we go, select outliers, and it's highlighting the row where that outlier is contained. But I'm going to actually make a note that we should really have a better outlier column to make that handy. Okay. Okay, so let me, I guess I'll just keep this here in case I need it again. Let me go to this data and just put this in a group and hide it from view, and pop that up there. Okay, so here's my fit that I'm going to work with. Again, this is my linear fit. Let's clone this. Now we're going to do the weighted version, and I'm going to calculate within the data table using an expression column the weight that I'm using for each row of data. So to do that, I'm going to click the button here to add an expression column. That adds my column, and over here is where I can specify what I want to calculate. And again, the weight value coming from NIST that they derived is the value for X to the 1.5 power. And, oh, sorry, 1 over that. There we go. So this is my weight. And then for this graph, I'm going to select that from my column here. So here's my, just make sure this is clear. Here's the weight. I'm going to select W. And it's subtle, but if you look now at where my line is towards the x-axis, it's doing a better job of fitting that data at the lower end of the x-axis because it's giving less weight to the data that's where I have more scatter in my graph. So it's a little bit of a better fit. And you can, compare these parameters to what they have in the NIST example to see these. You should be getting the same exact result as they have there using this weight. And I think that's it. I mean, actually coming up with the weights can be a little tricky, and they talk about that a lot in the NIST in the NIST webpage. And again, I don't have time to go into that because I need to get to our other examples. If there's any questions on that, please go ahead and let me know. I'm going to go ahead now and move on to looking at our next example that I want to do, which is the non-linear example. Okay, and this is the one that we're going to do. Actually, I want to, again, do this from scratch. So let me go ahead and bring you to this website where we're going to get the data. And this time I'm going to just send you the exact link on the chat for the data set that we're going to use. So this is the link that I just sent to you. This brings you right to the data file. And I want you to go ahead and copy this. So I just selected the data. I'm going to go back into, oops, sorry, go back into data graph. I'm going to do a new file, and I'm going to paste this data in. So same as before, data graph wants to make this a text column. I can actually just right click on the header of the column itself and say convert to number, and I'll delete this first column. And then I'm also going to do the same thing. I'm going to drag my X over to the left side. So I'll give you a moment to get that data. I hope I'm hoping people can follow along. Please let me know if you think I'm going too slow or too fast. Now for this particular data set, in the NIST file, the link that I sent you, they tell you the equation that they want to fit. This is the non-linear fitting example that I'm going to do here. And nonlinear curve fitting is where we can enter any arbitrary equation that we want. We're going to use the same command, the fit command. And this is actually an iterative procedure that is used mathematically to come up with the best fit option. Unlike the linear fit, which is an exact solution. So again, I'm not going to go into much more of the detail than that. You can find a lot of information on nonlinear curve fitting online. But what I'm going to do is use this same equation here. So if you want to sort of copy what I'm going to do here, I'm going to just select this y equal to, and it's an exponential term with a coefficient. This is the equation that we're going to use. Actually, I don't need to type the y part. I can just type the right-hand side of this equation. We'll just, again, do this the same way that they did in this NIST example. And same thing as before, I highlight my data set. I'm going to add the points now to view my data, and I'm going to add my fit. And by default, the fit command is always going to do the fit function as linear. So here's where you see where the fit function is. It's always going to be set to linear when you first add the fit function. Datagraph doesn't try and find, here's the best fit that you should use for this data. That's kind of up to you to select the type of fit that you want. Now, for this particular data, if you just want to look at some of these other options, it has a, quadratic, you can do a cubic, you can do any arbitrary polynomial up to these start to have some weird oscillations, but you can do very high order polynomial fits with Datagraph. What we're going to use for this is the arbitrary fit option. Now, again, why don't I go ahead and swap this so we can see this a little better. Now, what Datagraph does when you do the arbitrary fit option is it needs to have an equation to start with. So there's a function form that it shows. This is, let's see, here it is. So it just by default will put in a plus b and x to the squared, to x to the power 2. That's not the equation that we want to use. Clearly, it doesn't fit this data at all, but I do want to show you just a little bit of the mechanics of what's going on here when we choose an arbitrary fit. What Datagraph does is it automatically, I love that it does this, looks for our unknown coefficients. And that's what you see here. This A and B, Datagraph is just looking at this equation and saying, there's 2 coefficients that I need to fit for this data, and is setting them to an initial value of 1. So when you're doing nonlinear curve fitting, you always have to say, what is my starting value? Where am I going to start my fit at? And these may not be good either. Again, Datagraph is not trying to optimize for you what is the best starting value. You specify that, and that's, I think, pretty typical. But because what it's really doing is you have an initial guess at what that line looks like given A equal to 1 and B is equal to 1. And from that initial guess, the algorithm tries to find better values for A and B that actually will fit the data. Now for this is the best it can do. That line does not fit this data. So clearly this is not the right equation. What else can I do here? Oh, you can also say, I don't want to change. I want B to actually stay as 1, and I can uncheck it from being optimized. I can do the same for this one. I can also set limits. If I want B to only be positive, here B is being optimized to a negative number. There's a min and a max value I can set here. I can say, no, I want B to never be less than 0. So that gives me kind of even a worse fit. Just let me cut off my keystrokes here for the moment. So let me turn that off and put that back to where it was. And I think I still have the equation in my clipboard. So I just typed or pasted in that equation that came from the raw data. And I'm going to pause a moment and see if, again, people can kind of catch up. The chat is quiet, so I don't know if that's a good thing or a bad thing. But I really do hope that you can that I'm going at a pace where you can keep up. So what happened when I typed in this function form? Well, nothing happened. And the reason is that functions in data graph, we do have an exponential function, but it has to be lowercase. So I have to change this to lowercase exp, then hit enter. Now, data graph did exactly what it should do. It looked at this equation and it said, where do I have unknowns that are in this equation? Now, the only other thing is that, again, case sensitive, capital X is not what data graph expects in these equations. It expects X to be lowercase. So change those capital X's to lowercase x's. And voila, now we have a fit of the data. If you look at, and I guess I didn't send the link to you. I'm sure I have it somewhere somewhat handy, but I don't see it right now. So in the NIST page where they do fitting of this, they actually set their initial values to 0.1, which we didn't have to. We got a pretty good, we got a good fit even with an initial value of 1 rather than 0.1. When your initial values are close to the optimized value, then you're more likely to actually get a good fit. If I say my initial value here is, just give a crazy initial value. Actually, DataGraph's doing we've really worked hard to make sure that this does a good job of fitting, even when the initial value is actually kind of far from what it should be. Let me try, I think if I try a negative, yeah. So notice now you're not seeing anything. And there it is. Actually, that fit had failed. It probably should be showing the guess. So this right here, where this says draw guess, this allows you to see what the initial value or the initial curve is that it's trying to then optimize the coefficients for. So you maybe can't see it that well, but down here, there is a red line. And this is the line that results when you use this equation with these coefficients. That's really far from where the actual data is. This is actually the best fit line it's getting. It's doing a terrible job of fitting this data. So I guess it fit it, but it's it was able to get a value, but not a very good one. Now, if I set all my initial values to 0.1, which is what the NIST handbook recommended for this problem, see where that dashed line is, that dashed red line? That's the initial guess of getting close to what this equation looks like. So I also have sliders here where I can change these initial values. And again, even though this is fitting it, even when the initial values aren't always great, well, that's not too good. But if you're not getting a good fit to your data, then check your initial values and you can play with them here with the sliders to make sure that they are giving you, or that they are close to what the data looks like, somewhere in the neighborhood of the actual data. I'm going to put this back to only show the initial guess if it fails. Again, you have your goodness of fit parameters here. You can also add weights to the arbitrary fit function. And I don't think I have any. Are there any questions? Personally, I really like how this is set up, how it automatically detects the coefficients, how I can use these sliders to kind of play with the initial values. The optimized values are shown here, and also in the equation itself is shown here, where the optimized values are in that equation. And getting a little tight on time, but I really actually also wanted to show you, because when you're doing curve fitting, why are you doing curve fitting? Because you want to be able to predict what a value is, right? So I've come up with this equation, but I don't want to have to type that out again. I just want to use this equation to calculate, say, for example, I want to know, what the value is of y when my x is equal to 1. I want to get what that value is. So to do that, what you can use is a column called a plot action column. Let me go ahead and swap things back again and bring back my column list. So if I go over here and I say other plot action, so I'm over now in my side panel, I'm going to add one of these plot action columns. This functionality is probably something we added maybe about a year or two ago. But it's kind of an extension of what what various things in this column do. But basically, if I want to, let me add another number column. So these are my X data, for example. So, and I'll add also a column divider. So I have a number column where I can type in that number column, where do I want to calculate values along this set of data. So if I type in 1, 2, 3, 4, then I can say in my plot action, this is where I'm going to predict a y value. I can select this X data column here. The action in this menu, you're going to change this to evaluate. And then you'll see this function menu down below, and this will show you everywhere where you have a fit in the file. And I can then select this fit function. And again, my green arrows are making it clear which one I'm picking. So now I haven't had to type any of these coefficients. I've just used this fit in order to calculate for these given X values what the Y value is. And if you want to just double check and make sure that these are correct, I could plot these points. Let me give them a different color so you can see exactly where those points are. That I think is a really handy functionality, again, using the plot action column to do that. What did we do? We did the linear, we did the weighted, we did the nonlinear. There were two other things that I wanted to show you, and one is a LOESS fitting, and the other one is the multivariable fitting. So let me do a quick demo for each of those. And for that, I will use, I'm pretty sure I have a LOESS here that I can use in the online examples. Here we go. So if you type in LOESS, there are several examples of LOESS fitting within the example files. And the point of this type of fitting is to give you a way to represent a functional form for a set of data where the function otherwise would be very difficult to determine. What is the function that goes along with this? Well, I could do, multiple polynomial fits. But if I'm really just interested in showing the trend of the data, as opposed to, having a specific equation, then LOESS is a great way to go. When I was doing a lot of plotting of COVID data, for example, I was using LOESS often to smooth out, daily data that had a lot of random noise in it. And to do this, just like we did before, I'm going to do points. I'm going to do a fit. I'm going to change now my fit function from linear all the way down at the bottom. You can select LOESS. And there's really a couple of different smoothing options here, or I guess a total 4. But if you go to this menu, smoothing menu, notice that, oops, sorry, There's two on the two options on the top that say first and options on the bottom that say second. A LOESS fitting is basically a low order polynomial fit that is going all across your data. Again, so it's not, we're not outputting an equation for this. There's actually all different equations that are being used to represent that trend. But when you're calculating the LOESS fit, or the algorithm that does this can either use a first order polynomial or a second order polynomial. So if you choose second, you're going to get a slightly more curvature in your resulting trend line as opposed to first. And to be honest, sometimes I've had data where I feel like it does better with the first order, and I've had other data where I feel like it does better with the second order. I think it's something that you kind of play with. If you choose the slider option, then that gives you a way to kind of easily tweak what the trend looks like. Let me actually make this line a little bit thicker to make sure that you can really see this. So you can play with the trend. If you, and what LOESS is doing is it's basically a window. It's windowing, I think that's the right term, throughout the data set to determine how many points is it going to use to base these low order polynomials on to get this trend. If you want to specify exactly what that window is, you can use the option of where it says radius. By default, we use 1/3 of the width, 0.3 times the width. If you want this to be lower, you can type in a lower number, or you can type in exactly what you want the window size to be. So if, like for here, you know, if I want the window to be 0.5, I can just type in 0.5, and then it's going to have that moving window moving across. I often use the sliders unless I really want to be consistent between different data sets. Then I will type in exactly what I want the radius to be. So that's the LOESS fitting. Oh, 1/3 of what width? The width of the data set, the entire data set is what that means. So that can be helpful too. That's kind of a common rule of thumb that people will use, is to use 1/3 of that. The last thing, I'm going a little bit over, but the last one that I want to show you is the multivariable. I actually had a cute example for this, but here we go. So there is an example file. It looks like I only have this one here for multivariable fitting. And this is where you have multiple X values that you want to evaluate for how well they will predict another predictor variable. So if you go to this example file, the multivariable fit file. Oh, and there's other examples here of other fitting that we talked about. This is a made up example, but it just shows you how I have one Y value that I'm trying to predict with multiple X values. And what's kind of cool about this is, you know, if you think of a 2D plot, 2D plotting allows you to have an X value and a Y value, but here I have multiple X values. How do I represent that? If I have just a couple, I could do a surface, but when I have a lot of different X values, it's hard. It's multidimensional. You can't represent that. Let me just show you from scratch how this fit is created and explain what this graph is doing. So if I just add a new graph and I go to the draw menu, all the way down at the bottom, you will find the multivariable fit. This is a different command. You can go ahead and add that. And this one doesn't have, you don't select data and auto-populate. Maybe we should sort of have that as an option, but you can select what the Y value is that you're trying to predict. So in this case, it's this column here. But to add the X's, you can manually add them one at a time. There is a little plus symbol right here that you can click and add these X's, and then this gives you a menu where you can select them. But let me show you a much easier way. If you go over to the the side panel, select the values that you want to use in your multivariable fit. So not the Y value, but all the X's here. And I'm just going to drag these all at once. You can see there's a little icon that forms as I'm dragging this, and drop that right on the command, and it auto-populates that. So now it did the fit. You can do arbitrary fits here as well, but this is just doing a linear scaling of this data. And so what this is doing is it's allowing you to view X, a given X with Y, and you can pick which X you want to see. So currently, this is drawing this is drawing X1 and Y1. But I could change this with these toggle buttons to draw X2 with Y2 and X3 with Y, or X2 with Y, or X1 with Y. And when you do that, you can sort of see right away for some of these, does there look like there's any trend here? Not really. Does there look like there's a trend here? Yeah, that looks like there's a trend. It can be deceiving. Sometimes you might not really see a trend, but there's still maybe a relationship between the two. You can see the coefficients here for each of these. But for these, for example, my X3, the coefficient is very low, and there doesn't appear to be any relationship of X3 with Y. So if I'm creating a model, then it doesn't look like X3 is a parameter that makes a big impact on my model. And if I look here, I can see the R-square value. And if you uncheck any of these boxes, it will remove that variable from the model, so you can see what the impact is of that. So if I take away X3, I'm toggling it now back and forth. My R-square value does not change at all. So X3, that column, clearly isn't having a big impact on my result. So it's kind of cool because you can just very quickly check and uncheck these different parameters and include them or not include them in the fit to see what the impact is of your overall fit. And in the graph itself, the graphic, what it's doing is it's showing you the data point. So the data point here is in black, and the fit to that data point is the white point. So you ideally want these 2 points to be really as close to each other as possible when you're doing the multivariable fitting. Okay, so I went a little over. It's sometimes hard to fit everything in that I'm trying to do, fit everything in. Thanks for watching. If this video was helpful, please go ahead and give it a like. If you have any comments or questions, you can feel free to put them in the description of the video, or you can email us, help@visualdatatools.com. Until next time.